All right, it's recording. Exercise 13A and 13B. We're going to revise pretty much everything you've learnt about probability from year 7 to year 11. Let's see what you remember. Key terminologies. Sample space is the set of all possible what? Let's go, Ryan. What do you think it could be? What's a sample space? Outcomes. Outcomes means like results. Okay, so for example, if you roll a dice, all the possible outcomes are 1, 2, 3, 4, 5, 6. PR, open brackets, event, close bracket. Event means the chances of what it is that you're looking for. We call that an event. So hence, number of favorable outcomes. So what you're interested in out of the total possible outcomes. Probabilities are expressed as decimals or fractions between what values? Something and 1. What goes there? Let's go with Tara. 0 and 1, because you can be 0% sure or you can be 100% sure, which is why it's 0 and 1. Sum of all probabilities of an experiment is equal to what? Let's go, Rango. 1. Because we already said max is 100%, so if you add them all together, it should equal to 100%, which is 1. Hence the addition rule. Let's see how many people remember this one. What's the addition rule? Which is PR of A union B is equal to PRA plus PRB minus what, Neil? Intersection. Very good. Which makes sense if you think about it on a Venn diagram sense. If you take A plus B, so if I did A and I plus B, I'd end up doubling the center. So hence I have to subtract the overlap, which makes sense. Union is the set of all outcomes that belong to B events. Both events. That's true. I was just thinking what I wrote. I'm like, what's B events? Both events. That is true. Includes all or unite, whilst intersection, which is different, is the set of all outcomes that are common. That's what the word intersection usually should remind you of. So intersection and common. Union is, I like to think of uniting. So both events are uniting. Then, mutually exclusive. If both events cannot happen at the, it means, mutually exclusive means if both events cannot happen at the same time. Which means they can't happen simultaneously, right? So they're both... Exactly. You can't roll a 1 and a 2 at the same time is a good example of that. So hence, by definition, mathematically, probability of getting A intersection B if it's mutually exclusive is equal to 0. Very good. There is no chance of you rolling a 1 and a 2 at the same time with one dice. Hence, for mutually exclusive events, the addition rule now becomes what? PR of A union B is equal to, let's go with Samuel. Is it 1? Yeah. Oh yeah, I guess you can. Well, it depends if there was something outside of it too. I'm not sure if it's definitely 1, but I do know, so the addition rule, which we said before, was probability A plus probability B minus probability of A intersection B. But if we know that they're mutually exclusive, then what changes? Albert?
It's just probability A plus probability B.
Correct. Now, naturally, I did think, it could have equal to 1, but it depends on the Venn diagram. There could have been something outside of A and B. So had you had A was this, and then B was this, so let's say 10, 5, and then 7, then it wouldn't mean that its total probability is 1. Yeah? So, very good. I'm just going to highlight that one. So A union B, if it's mutually exclusive, A probability A plus probability B, because intersection is 0. Independent events. Events are considered independent, which, interestingly enough, in the exams, students think, or they confuse it with mutually exclusive, because we think living independently means you're separate from others. It's not the same. Independent events is something else. It is if the occurrence of one event does not affect the probability of another event. That's what we mean by independent events. Then technically in year 11, you did learn a way to prove it mathematically. Or when they ask you to justify its independent events, what do you have to do to prove that they are independent again? Anyone remember? Good, because you're going to be doing 13A and B. So there'll be parts of it where they'll ask you to do that. And remember, hands up if you know. Okay. Leave that for now, because I think I'm going to remind you. No, it looks like I didn't set it up for you. But I'll just leave a little arrow there. We'll do conditional, so then it links back to independence, because that's what we usually do. We do conditional before we do independence. And you see how they're both linked. Independent events, conditional probability is the chances or likelihood of an event occurring given a previous event has already occurred. Can you see the difference between the definitions? That independent and conditional are actually opposites of each other. One says does not affect the chances of another event, and the other, it does. See, the other does say one event does affect another event. Now, conditional probability from last year, you would have seen this formula. Probability of A given B is equal to probability of A intersection B divided by probability of B. Now, it's probability of B because you already know B had occurred. So it's only within that sample or within that population. And then whatever you're interested in, A and B has to occur at the same time. So you're looking for A, given that B had occurred, so it's intersection of A and B, right? But by rearranging that formula, notice that if I times both sides by probability of B, I end up with this rule. This is very similar to the multiplication rule. Do you remember the multiplication rule? Probability of A intersection B is equal to PR of A times PR of B. Now, this one, when you learnt it, they never told you in year 7 to 10 that technically they were using independent events. It just so happens that the things you were doing from year 7 to 10, they were independent events. Like flipping a coin, rolling a dice. It doesn't matter how many times you roll that dice, the chances of getting a 3 or what you got before does not affect the chances of the next one. So if I flipped a coin and I got 10 tails in a row, it doesn't mean the next one I have a high chance of getting heads. It's still 50-50, right? That's independent events. So this is one of the reasons why most students don't realize when it's independent and when it's not. See the difference between conditional, and I'm going to show you diagrammatically so it makes sense to you. This is the independent rule. Last year, that was exercise 9G. This is 9F. Yeah, so in your year 11 textbook. That's conditional. That's independent. And the only difference between the two is this bit, the given. So if I draw a diagram for you to see, this is what they're essentially saying. If B had occurred first, so given that B had occurred first, you're saying this. You either got B or you didn't get B on the first go. Then the next branch is my second go, let's say I flip a coin, then my second go is the chances of getting A, or I might not get A. A, not A. True? When you do the branches back in year 7 to 10, you would have said chances of getting B on the first go. So let's say that was, 1/5. And then, so you got 1/5 of chance or 20% chance of getting B. Then when I say chance of getting A, this is where it's important. The second step depends, the chances of getting A, let's say I said it was, 1/3. Is this 1/3 chance, the 33% chance, affected by B or not? Okay, if it's not affected by B, that means chance of getting A is always going to be 1/3. Doesn't matter, right? Every time you flip, it's going to always be 1/3. But if it does matter, if me getting B affects whether I get A or not, that becomes conditional. So what changes in your multiplication? You still multiply them. You still do 1/5 times 1/3. But you see the notation's different. This is probability of B times, this is probability of A, but it's not just A by itself. It is A provided that you got B to begin with. Because if you didn't get B, it changes the probability of getting A. So that was conditional. That's why this branch brings you to this formula. Whereas in independence, if it didn't matter whether I got B or whether I didn't get B, and both of them is still 1/3, then what I'm saying here is I'm saying probability of chances of getting A, whether you got B or not, doesn't matter. It's still the same as getting probability of A. That's why just that little small difference, and that's one of the definitions in your textbooks for independence, if I then replace it, that is just probability of A, that's how you get this one. Probability A times probability B, that's B times the A, that's the same thing. So this small minor difference is based on the conceptual difference. Is A, the chance of getting A, is it because of the B? Does it affect it? Because if it does affect it, that means this one will be different. But if it doesn't affect it, that means this is both always going to be the same. And that's what chapter 14 is. 14 is making the assumption this will never change. That each time you roll the dice, or you do whatever the event is, it's always going to be the same each one. And because it's the same, it's predictable. It means that you can then come up with a formula, and that's what you're learning in chapter 14. Yeah? And then when it's different, that's where you have to do other techniques. Rango, you had a question?
Oh, no, that was you guys.
Okay. Yeah. Okay, so it sounds like a small thing, but I really think it's a core part to understand when to use them. So in your exams, if they give you independent events, it's this one. They're telling you that each event has no effect on one another. This is the formula you use to prove it. If it's conditional, which I gave you an example on the next page, so you can see this is the one you're using. Same diagram, just different in technicality there. Okay? All right, and that was pretty much, that bit there was the year 11 bit. This is the only part that was year 11 probability. The rest was 7 to 10. Yeah? Some other tools that you would have learnt along the way. You learned tree diagrams, which I just drew one for you to see. Multiplication rule comes from that tree diagram. And then another one is visual aids like Venn diagrams, Carnot maps, which is technically a two-way table. I highly recommend, if you haven't been practicing with Venn diagrams and Carnot maps, use Carnot maps. Your exams, especially the one, I'll show you in the next example, your exams when they start giving you PR of A and then PR of A, complement, whatever, this is the general approach to solving it. Okay, so learning how to use a two-way table is going to be useful for you. Okay? All right, let's do some examples now. So if you zoom out, that's pretty much your year 7 to year 11 probability conceptual knowledge. And then we're going to take that and apply it to each chapter based on the different data that we get. Let's flip over the page. Let's look at the example 1. I'm going to pause the video. I'm going to give you 5 minutes to have a go. It shouldn't take 5 minutes, but let's see if you can answer this using the tools in the summary of the previous page. Can you use your current knowledge to answer these questions? The next one. So next one, scroll down to example 2. All right, here we go. Let's go. Did you get for A? 0.7, 70% chance that he'll lift a personal best. So I just drew a tree diagram. I know it's conditional probability. Each lift is dependent on the previous ones, whether he ate a banana or not. So 0.4 if he didn't, 0.9 if he did. And then therefore 0.1 that he wouldn't lift a personal best, and 0.6 he wouldn't. So tree diagram first is what I do. And the question was, what's the chance of getting a personal best? Well, there's 2 ways that you can get a personal best. So hence you have to calculate both scenarios. B dash times L, and then B times the L. Add them together. I get a 0.7. Hands up if you got 0.7. Okay, that's conditional. So if you were struggling with that one, that's conditional probability. Same thing with the next one. B, you didn't have to do much calculation again. That's L dash, so it's the complement. So it's just 100% take away 70%, which is 30%. Okay, so it's a quicker approach rather than doing conditional probability again. That would have been quicker to get L dash. And then lastly, chances that he ate a banana in the morning, given that he lifted a personal best in the gym. So if we knew he had a personal best, our chance of a personal best is 0.7. Then chance of eating a banana and lifting a personal best is 0.6 by 0.9. Overall is 27 to 35, or roughly 77% chance that he would be able to, that he actually had a banana in the morning. Okay. I'm going to stop the video there.